All right.
And the advanced was, here's some interesting things.
Yep.
So, this is an odd question, but do you have any hexagon wrench?
Hexagon wrench, you mean just like Allen wrenches?
Yeah.
Yes, we have Allen wrenches. Ask Max and we'll...
Yeah, my car broke down and the wires for the battery like broke off. So like maybe solar just put it back in.
Okay, we'll see you at the at 4 o'clock. We'll see.
I hope I still have a lot of parts.
Yeah, we'll see if we can fix you up. All right. So we're going to the things that happen. All right, so we are going to do op-amps. You guys are going to find this useful for the next coming lab because we do a lot of filtering. The next lab is filtering, so we're going to do sensors and then filtering, and then I think that's the order we do it in. I might do filtering next, then sensors. I'm not sure yet, depending on what you need. You kind of need the basic sensors just to know how they operate. All right, so op-amps are sort of the building blocks of signal conditioning, and we one of the nice things is they are linear, very linear, which is why we like them. So in general, the signals coming in from the sensor are in the millivolt range, right? So that would be the signals. And what the microcontroller wants to read is in the volt range. So we need something that can amplify from one to the other. So here's where, right, we want to gain, right? We just want to boost the signal, just raise it up. Filtering is in terms of, this is getting rid of frequencies that I don't want and amplifying specific frequencies that I do want. So for instance, in the case of the lab that's coming, and these are the beacons that you'll use on your project, right, we have a 2 kilohertz wave that's coming in at a 50% duty cycle. Right? So we have a square wave that's coming in, and this is running at 2 kilohertz, and it's up for 1 thousandth of a second, so this is 1 millisecond, and then down, and then up, and then down, and up, and all the way down. Sorry, that would be a point. It's a, this is 0.25 milliseconds, and that's 0.25 milliseconds. All right, so the idea is, now, a square wave, unfortunately, contains all frequencies, right? Because a square wave, now it's not a perfectly square wave. If you look at it, it's, it's got rounded corners on it, so it doesn't quite have, it doesn't go up into the terahertz range. But it's got a lot of higher frequencies on there that you're going to want to get rid of. Likewise, it's got lower frequencies. But underneath this, the 2 kilohertz modulation means that fundamentally I want to isolate that 2 kilohertz signal and see if it's there. All right? And so what I want to do is get rid of everything that isn't 2 kilohertz. There's specifically there's 2 things I really want to get rid of, all right, if I can at all. One is the, was that DC, correct? So I don't want it to change how it works between daylight and nighttime. So that's about as close to DC signal as I get. All right, so it changes on a 24-hour period. The other one is the fluorescent lights tend to oscillate at about 220 hertz, and so you want to let Max in? All right, and lastly, there are tricks I can do with this. So I can do some nonlinear tricks with these, things like rectification. I can do multiplication, peak detection. There's a few other things we can do with it. So there's a lot of nonlinear ones we can do with the op-amps as well. All right, so very quickly, the op-amp is a 2-input device. For historical reasons, the negative one on the top is referred to as the inverting input, and the positive on the bottom is the non-inverting input. Okay? And essentially they are, it operates as a difference amplifier, which is to say that Vout, so here's Vout, so Vout equals to some gain times V plus minus V minus, right? That's how they work, right? And for your run-of-the-mill vanilla 2-cent op amp, uh-oh, we're going to get kicked out. Yeah, you guys are, you guys need it? Yeah. Okay. All right, so we'll, are you going to be late at all? No. All right. We're going to have to, let me stop this and see if I can find another, the audio together. All right, so we were talking about the fact that we are at, so a standard vanilla cheapo op amp that you can get for, $1 has a gain of approximately 10K, 10,000, right? 100,000 around there. So quite big, which means that if you ever hook it up, so we never use it like this, right, as an open-ended thing because it will sit on either one rail or the other, right? Typically, it has so there's also a supply here. Now, they'll often be written as plus V and minus V for a double-ended supply, so we can go above ground and below ground. As in this class, and I would strongly recommend in most of the applications you do, tie the bottom end to ground. All right. If you find yourself needing to go below ground, yeah, kind of rethink your circuit. And we'll use in this class, we'll use them at either plus 5 volts. Some of them go up to 18 volts, 20 volts, so you can do them. The one we've given you a bunch of goes up to 6 volts. So above that, it will get unhappy. So plus 5 is a good place to run them at, or 3.3. That one will, in fact, work all the way down to, I think, 1.8 volts. So it'll work quite well. And, of course, we want to bypass cap them always, right? Especially your op amps. So you always want a capacitor right across, literally right across the power and ground. You want the leads to sort of straddle the chip. All right, so it's right there. And if we use it like this, then what we wind up with is if V plus is greater than V minus, then V out is whatever my supply is, right? And if V minus is greater than V plus, then V out is equal to ground. So they're not terribly useful this way. So the way we always use them is in, we always use them in negative feedback, which is to say we tie something from V out and tie it to here, whether that's a resistor or a capacitor or an inductor or any other number of things. We always use it with a path back from the output to the negative input. And that will stabilize it and actually allow it to get to any circuit. All right. Unlike what people in education say these days, negative feedback works, positive feedback does not. All right. The only time you ever put these in positive feedback is if you want to change it from an op amp to a comparator, where you want it to essentially fly from one rail to the other as quickly as possible. All right. And there are reasons to do that as well, which we can get to. Okay. So, golden rules of the op amp. Okay. So the golden rules are that the inputs draw no current, and that the V out moves in such a way that the V plus and the V minus are always at the same potential. All right, they never change away. And again, it only applies if they're in negative feedback and within the listed specifications. All right, and for the op amps we've given you, the specifications have gotten a lot better. We used to give you a different one called the LM324. And the LM324, when operated off of a 5-volt rail, could only get to V out was 3.5 volts. All right, it sort of left 1.5 volts on the table, but it just couldn't get up to, which the one we've given you is a nice rail-to-rail op amp, so it's a pretty good one. All right, so now we're going to show you how to analyze things using these ideal op amps. So for the ideal op amps, we basically consider the gain to be infinite, and the inputs draw no current. That is, no current flows into node A or node B. All right, so let's look at the inverting amplifier. So what we've got here is this point here is 0 volts. Right? It's 0 volts because it's tied to ground. That means that this point is at 0 volts because, according to the rules, the two inputs are always at the same potential. Okay? We also know that it draws no current. So whatever current flows into here is the same current that flows there. So now let's figure out what we've got. So I've got that Vin minus 0 over R1 is equal to I, and I've got that 0 minus V out over R2 equals to I. So if I set those two together, I've got that Vin minus 0 over R1 equals 0 minus V out over R2, all right, or I've got that V out over Vn is minus R2 over R1. And this is what we call the inverting amplifier. And the reason it's an inverting amplifier is that it's a negative. All right? Now, of course, you say, well,
why is it an amplifier?
because I can make this, the R2 and R1 don't need to be equal. Right? So if R2 and R1 are equal, well, then it basically gives me the inverse of the thing. But if R2 is 10 times R1, right, then I get a gain going through the thing. That's why it's an amp. So these are called operational amplifiers, op amps. So it's always an amplifier. This could attenuate. So the inverting op amp can do both amplification or attenuation, right? Which brings us to the non-inverting configuration. All right, so non-inverting configuration, Vn goes here. So this point here is also at Vn. All right, so now again, and this point is at 0. All right, and again, because no current flows in, that I is that I. So again, we're just going to use V equals IR, and I'm going to say 0 minus Vn over R1, I'm just going to go ahead and equate it, is equal to Vn minus V out over R2. All right, and so I'm going to get an, this is going to be an R2 minus R2 V in is equal to R1 V in minus R1 V out. Let me do a V out, R1 V out equals to R1 plus R2 times V in, or V out over Vn is equal to R2 plus R1 over R1, or 1 plus R2 over R1 equals V out over Vn. And that is the formula for the non-inverting op amp. Now notice that the minimum gain I can get on this is 1. Right? I can never get below 1 on the gain. Right? So that's one thing. And the output moves in phase with the input. As the input rises, the output rises. On the inverting one, as the input rises, the output drops. Right? So I have these opposite directions. Okay? And the other thing is, let's look at the corner conditions. What happens if, now the nice thing is, because Vn is going straight into the positive terminal of the op amp, it means that this thing has, essentially it's a current wall, right? No current can flow into the op amp. So this is a nice impedance wall. So no current can flow through all, so you're not loading whatever's on the upstream of V1. All right, so if you have a sensor, for instance. And what if R1 was infinite and R2 was 0? In that case, I would have something that looked like this. I would have V in and V out, right? And this means that V out equals V in. And this is called, that's correct. So this creates a wall between the current. So all the current for V out, so V out follows V in up to about at least a megahertz, right? At some frequency, it'll eventually start falling behind. But you can rely on this for up to about a megahertz. If you need to go faster than that, there are better op-amps you can buy. But no current flows, so V in, so all the current that goes in V out is supplied by the op-amp. None of it is supplied by the input. So you've created an impedance wall between the two, right? So there is no flow across there. All right? So that can be a very useful thing. And that, by the way, is called a buffer, or a unity gain buffer. Right? So it's made to basically separate the two halves of the circuit. So what goes on up here does not affect what goes on out there, other than the fact that the voltages track. All right. So let's look at a quick example here. Okay. So I've got V in goes between, so V in peak to peak is 200 millivolts. Okay? And I want V out peak to peak down here. I want it to be 2 volts. And I want it in phase with the input. Okay? So in this case, right, I say that this is, so first of all, what's my gain? Right? My gain is 2 volts divided by 0.2 volts, so I need a gain of 10. Right? And because it's in phase with the input, I need a non-inverting configuration. Right? I want them to go in phase. So that means that I have here, I've got V in goes in, and here I've got V out, and I know that 1 plus R2 over R1 is equal to my gain. Right? So that means that R2 has to be 9 times R1. Right? So what are 2 typical values that I want? So I'm going to go look at my 5% resistor table, and I'll pick out 2. And so I'm going to say that R1 is 2 kiloohms and R2 is 18 kiloohms. All right? Both of those are standard values within the 5%. Now, why am I using kiloohms as opposed to 200 ohms? Right? Turns out that I don't want to. So generally with op-amps, so a couple of rules of thumb. Don't be greedy on the gain. Try to keep your gain sort of in the 10 and below area. If you need a gain of 1,000, go through 3 stages of 10 each, not one shot for 1,000. You find that when you try to boost the gain really, really high, you wind up getting a very twitchy circuit on your hands. The other thing is try to keep your resistor values in the kind of the 1 to 100K sort of range. Try to avoid mega ohms and try to avoid anything lower than a kiloohm. All right, just as sort of rules of thumb, and you'll be okay. Okay. Now, so here's the formal one, right? Looking like that. So let's do a slightly different one, all right, that we're going to do. Okay. So here we've got, I'm going to go from 0.9 to 1.1 volts. So my peak to peak, V in peak to peak, right, is 1.1 minus 0.9. So that's the same 0.2 volts. And my V out, peak to peak, goes from 0 to 1 volt, right? And I want it 180 degrees out of phase. All right, we'll get to that in a second. So this is 1 volt. So my gain is what? Right. So my gain is 5. And because I want it out of phase, I'm going to be using the inverting amp. Right? So I'm going to have this. So Vn is going to come here. Right? And this is R1, R2. And I know that the gain is equal to R2 over R1. Right? It's minus, which means the phase is 180 degrees. Right? And so in this case, I need the R2 equals to 5R1. And in this case, let's do a 10 kilo ohm and a 2 kilo ohm resistor. So we're good on that one. Now, the interesting question is, I want it to go from 0 to 1 volts. Right? If I tied this to ground, that wouldn't work. But there's nothing special about this point. We just need to figure out what that point has to be in order to make our op amp get to where we want to go. So let's think about it. Since it's going to be out of phase, all right, at the top, at 1.1 volt, my output should be at 0 volts. All right. Likewise, at the bottom, at 0.9 volts on the input, my output should be at 1 volt. Right? Yes? Okay. So now all I'm going to do is, I already know what the resistor values are. I know what Vin is. I know what Vout is. Right? Let me go ahead and solve for what that has to be. So I'll solve it at one or the other. I'm going to do the one at Vout equals 0 because I think that one's an easier one to do. All right. So let's do it 1.1 volts. So I've got 1.1 goes through a resistor and it's a 2 kilo ohm resistor, 2 kilo ohms, goes to, let's call it V plus. All right. Then it goes through R2, which is 10 kilo ohms, and it goes to 0. Right? Well, this is nothing more than a voltage divider. Right? So we know that Vout of a voltage divider is equal to R2 over R1 plus R2. Right? Times Vn. So in this case, this is 10 over 12 times 1.1. Right? And if I did that right, that should mean that V plus, right here, should be set to 0.917 volts. How do I get that 0.917 volts? I put a voltage divider on it, right, to get it there. And then, as it rises, when it hits 1.1, the output will go to 0. Right? When it falls all the way to 0.9, the output will rise up to 1 volt. You can always do this, right, with an op amp. All right? So anytime you have so you say, okay, what's my input bounds from where to where, and what do my output want to go? Right? And as long as they're consistent, it will come up with a gain and an offset, and you'll be able to calculate whether you want it in phase or out of phase and how you do it. Now, the disadvantage of the inverting op amp is that I'm loading my whatever is generating V1. Right? If it's a non-inverting one, then V1 goes into the hit straight in, and so I'm not loading it at all. Right? So that can be a little bit better. Here are the exact calculations, and there's 0.17, and you can do it both ways. Right? I chose to do it at this point, but if I did it at this point, the 1 volt, I would get exactly the same results. Right? And it always works that way. Okay, we talked about the non-inverting buffer. Already did that, and so nothing more needs to be said there. Yeah. Yeah.
So yeah, it lets you track voltage.
Yep. Up to a point, right? Up to a point that's called the unity gain bandwidth. Right? Yep. So the gain bandwidth product is as high as you can go on there, and really you should be a little less than that.
All right, but what are the applications of that? Like,
oh, you put this everywhere. You put this. So, for instance, if you have several stages of filtering and you want one not to affect the other, you stick a buffer in between. right? If you have a sensor that can't be loaded, that can't put a whole lot of current in, and you need current on the other side, you stick a buffer in between, right? So the idea is you sort of stick it. What's that?
Op-amp provides as much speed in the current.
Right. The op-amp supplies all the current,
Right.
not the sensor.
Okay.
So the idea is that if you have something you don't want to load, then you do that. A couple of things here. So the input impedance. So think of Vn goes through a resistor to ground, and a typical op-amp R is very, very large. So think approximately 10 mega ohms. All right. And likewise, that's the input impedance. That's what we said when it's an input wall. All right. It's a very, very big resistor, therefore very little current is going to flow through that. All right. Likewise, the output impedance, it's got some source resistance here that tends to be pretty small. Right. However, you have to take it into account when you load it, right, to make sure it can deliver you enough oomph, all right, to go. And there are specs. And let's see. Okay, signal conditioning. All right. So like we said, we can if we do this, all right, then so here's my phototransistor. And if I set it up to here, I've got 0 volts here, 0 volts there, right? Whatever current flows this way, which is called IC on, which is the amount of current that flows. It's proportional to the light that falls along the base, all right? And V out is going to be equal to minus IC on over R, all right? Now, there's a slight problem there, and that V out is negative, right? You say, okay, well, that's fine, but there's nothing magical about this ground. So instead, let's get rid of that and put 2K, 2K. This is now at 2.5 volts. That's at 2.5 volts. I'm still holding it at a constant potential, right? And V out is now, at this point, 2.5 minus IC on over R, right? So I've just shifted the whole equation, right, by doing that. Okay? So that's a useful one. Couple of other op-amp tricks, and then we'll be done very shortly. So this one is kind of an interesting one. All right, so what does this one do? So let's take a look. From V2 to ground, I have a voltage divider, right? So here I've got, this is V2 goes through R1, goes to R2 to ground, and there is V plus. So V plus is equal to R2 over R1 plus R2 times V2, right? That's what the voltage is right there at this point, okay? Which means that's what the voltage is right there at this point, okay? So now I have my current flowing in through here is going to be the same current flowing throughout there. So what I'm going to do, so let's call that VB, right? And VA is equal to VB, right? So I've got that VA equals VB equals to R2 over R1 plus R2 times V2, all right? And if I go ahead and now do the current flowing through here, that means I've got V1 minus VB over R1 is equal to VB minus V out over R2, right? But I know what VB is, so the math is going to get a little bit messy, right? But not too bad. I've got V1 minus R2 over R1 plus R2, V2 divided by R1 is equal to R2 over R1 plus R2 of V2 minus V out all over R2. And now we start cross multiplying. All right, and I get V1 R2 minus V2 R2, right? Because the my V1. All right, we do a lot of little. So I'll leave the messy algebra to you guys because I don't want to keep too long. But in the end, what I wind up getting is that V out is equal to, when all is said and done, V out is equal to V2 minus V1. Right? So this is a difference amplifier. Right? And you can also, and so this is basically, it says, hey, you want to subtract one from the other? This is how you do it. Right? Which is kind of pretty cool. Right? And from here, it's actually not that far. It's just I want to get to the other one. All right. So the last one, and by the way, the great way to look up, there's tons of stuff. If you look sort of on the web, you sort of amplifier applications, and in fact, the a lot of the amplifier data sheets have a whole bunch of applications on them. And you can just look, and they have sort of all of these various circuits. Oh, you want to do this. You want a difference between this resistance and this current. Do that. And it just goes, and it sort of can measure almost anything. They've got them there, and of course, they all use 1,000,000 op amps because then they sell you the parts. So the last one I have for you guys is this particular one, which is a funky one. All right. And now, the neat thing is, so at first you look at this and you're like, okay, how the hell do I analyze this? And the answer is superposition, which is assume V1 is V1 and V2 and V3 are 0. Analyze it. Go back and assume V2 is something and V1 and V3 are 0. And go back and assume that V1 and V2 are 0 and V3 is something. Analyze it, and then add the results together. Right? That's what linearity means. Linearity holds. Superposition holds. So if I look at this and if I ignore V2 and V3, I say, wait a minute, this is just a inverting amp, right? So I'll say, look, this is going to be 0 right here. So I'm going to assume V2 equals V3 equals 0, right? Which means that V1 minus 0 over R1 equals to 0 minus V out over R1, or I've got that V out equals to minus V in, right? And the same is true for each of them, right? So in the end, I've got that V out is equal to minus V1 plus V2 plus V3. So this is called a summer. Right, so this one I can do, I can actually take the sum of all of them. All right, and then just add them all up together. Right. Right, the resistors won't be perfect, although if you were doing this, you might consider using 1% resistors that are more closely matched. Or, as long as you took 4 of them from the same manufacturing batch, they'll all be pretty damn close, even though they might not be exact. But the fact that you're using them in 4 places means that they'll all be quite tightly matched.
So the same batch will tend to have the
same match will tend to have very little variation among them. They've gotten very good at making relatively little variation. Okay, so that is all I had for you guys on op amps. We'll stop there, and I will stitch these all together.